Imagine standing in a world where the ground trembles beneath your feet, not from earthquakes, but from the thunderous footsteps of creatures so massive they could peer into fourth-story windows. Picture forests where the trees themselves seem dwarfed by the towering necks of giants that stretch impossibly upward, their heads disappearing into the clouds. Envision skies darkened not by storm clouds, but by the leathery wings of reptilian behemoths spanning the width of small aircraft. This was Earth during the age of dinosaurs, a realm so alien, so magnificent, and so utterly dominated by these extraordinary creatures that it challenges not one is our very understanding of what life on our planet can become. For 180 million years, an almost incomprehensible span of time, dinosaurs ruled every corner of the terrestrial world. To put this into perspective, modern humans have existed for merely 300,000 years. Our entire species, from the first Homo sapiens to the present day, represents less than 0.2% of 1% of the dinosaurs' reign. Recorded human history, the entirety of civilization from the first written word to this very moment, spans a mere 5,000 years. The Roman Empire, which we consider one of history's great enduring powers, lasted perhaps 1,500 years at its maximum extent. The dinosaurs' dominion exceeded this by a factor of more than 100,000. They witnessed continents drift across the face of the earth, watched as mountains rose and eroded away, and adapted to climatic changes that would make our current concerns about global warming seem like minor fluctuations. This is their story, a tale of humble beginnings, explosive diversification, absolute dominance, and ultimate annihilation. It is a story written in stone, demoed by scientists who have dedicated their lives to understanding these vanished monarchs of the Mesozoic era. Through their fossils, we can reconstruct not just their bones, but their lives, their behaviors, their triumphs, and their final catastrophic end. This is the chronicle of the rise and fall of the dinosaurs. For one, to understand the rise of dinosaurs, we must first understand the world they inherited, a world still reeling from the greatest catastrophe in the history of life on Earth. The stage was set approximately 252 million years ago, at the boundary between the Permian and Triassic periods. This moment in geological time witnessed the Permian-Triassic extinction event, colloquially known as the Great Dying, and the name is horrifyingly appropriate. The numbers are staggering beyond comprehension. Approximately 96% of all marine species vanished. On land, 70% of terrestrial vertebrate species disappeared. For the only time in Earth's history, insects experienced a mass extinction, with 8 out of every 9 insect species perishing. The planet's forests were devastated, with many regions transformed into barren wastelands. The fossil record shows evidence of what paleontologists call a coal gap, a period of millions of years when no significant coal deposits formed because there were too few plants to create them. What could cause such apocalyptic destruction? The evidence points to a perfect storm of catastrophic events centered around massive volcanic eruptions in what is now Siberia. These weren't ordinary eruptions. The Siberian traps, as they are known, represented volcanic activity on a scale that dwarfs anything in modern experience. Lava flows covered an area larger than the continental United States, in some places, piling up more than 2 miles thick, but the lava itself wasn't the primary killer. The eruptions released enormous quantities of carbon dioxide and other greenhouse gases, triggering rapid global warming. Ocean temperatures rose dramatically, and as water warms, it holds less oxygen. The result was widespread oceanic anoxia, where vast expanses of ocean became biological dead zones. On land, the increased temperatures and changed atmospheric composition created hostile conditions for most life forms. Acid rain fell. The ozone layer may have been damaged, allowing harmful ultraviolet radiation to reach the surface. Some evidence suggests that hydrogen sulfide from bacteria in the oxygen minus Depleted oceans may have reached toxic levels in the atmosphere. It was quite literally a hellish world. The extinction didn't happen overnight. The crisis likely unfolded over tens of thousands of years, perhaps even longer. But by geological standards, it was instantaneous. And when the dust finally settled, when the volcanic eruptions ceased, and the climate began to stabilize, the world that emerged was fundamentally different from the one that had existed before. The dominant land animals of the Permian had been the synapsids, particularly a group called the therapsids. These were the ancestors of modern mammals, though they looked nothing like the furry creatures we know today. Some were large predators with powerful jaws and saber-like teeth. Others were herbivores of various sizes, filling ecological niches similar to those occupied by antelopes, cattle, and elephants. Today, they were the ruling class of the Permian world. But the Great Dying hit the synapsids especially hard. Most lineages were completely wiped out. Only a few small survivors made it through the extinction event. And these would eventually evolve into true mammals. But that story would unfold much later. For the moment the synapsids were devastated, their dominance ended. Into this post-apocalyptic world stepped a different group of animals. The archosaurs. The name means ruling reptiles, and it would prove prophetic. Early archosaurs were relatively small, ranging from cat-sized to perhaps as large as a large dog. They had certain anatomical advantages that would prove crucial in the changed world of the early Triassic. Their legs, unlike those of many earlier reptiles which sprawled out to the sides, positioned more directly underneath their bodies. This allowed for more efficient locomotion and better supportive body weight. Their skulls featured additional openings, called fenestrae, that reduced weight while maintaining strength and provided attachment points for larger, more powerful jaw muscles. These might seem like minor advantages, but in the harsh competitive environment of the early Triassic, every advantage mattered. The archosaurs began to diversify, adapting to various ecological niches left vacant by the extinction. Some became aquatic predators, evolving into the crocodile lineage that survives to this day. Others took to the air, eventually becoming pterosaurs, the flying reptiles that would rule the skies for over 150 million years. And one group, initially rather unremarkable, would become the most successful land animals in Earth's history, the dinosaurs. The exact origin of dinosaurs remains somewhat mysterious, primarily because the early Triassic fossil record is frustratingly incomplete. The harsh environmental conditions meant that fewer organisms fossilized, and the geological processes of the last 230 million years have destroyed or buried many of the fossils that did form. But from the tantalizing fragments we have found, we can piece together the story of dinosaurian origins. The earliest dinosaurs appeared during the Middle to Late Triassic period, probably around 230 to 240 million years ago. They were small, rarely exceeding a meter in length, and were far from dominant. In fact, they were distinctly minor players in the Triassic ecosystem, overshadowed by various other archosaur groups. One of the earliest known dinosaurs, or at least a very close relative of the first dinosaurs, is Eoraptor, whose name appropriately means dawn thief. Discovered in Argentina in rocks dating to approximately 231 million years ago, Eoraptor was a slender bipedal creature about 1 meter long, with a long tail for balance. Its hands featured 5 fingers, and its teeth showed a mix of characteristics, some suited for eating meat, others for processing plant material. This suggests that the earliest dinosaurs might have been omnivorous, capable of eating whatever food sources were available. Another early dinosaur, Herrerasaurus, also from Argentina, was larger, up to 6 meters in length, and more clearly carnivorous. Its jaws were lined with serrated teeth, perfect for slicing flesh, and its powerful hind legs suggested it was an agile predator. Yet even this impressive hunter was just one of many predators in the Triassic ecosystem. What made dinosaurs? Dinosaurs. What anatomical features distinguish them from their archosaur cousins? The answer lies in subtle but crucial details of their skeletal structure. New dinosaurs had a fully open hip socket, a hole completely penetrating the pelvis where the leg attached. This allowed for a fully upright stance, with the legs positioned directly beneath the body, providing superior weight support and locomotion efficiency, compared to the semi-sprawling gait of many other reptiles. They had a distinctive ankle joint that functioned like a simple hinge, allowing the foot to move primarily in one plane, forward and backward, which is highly efficient for terrestrial locomotion. They possessed an elongated delta pectoral crest on the humerus, the upper arm bone, providing attachment for powerful chest and shoulder muscles. These features might sound technical, but they translated into real-world advantages. Dinosaurs could walk and run more efficiently than most other reptiles. They could sustain activity for longer periods. They were, in essence, better designed for terrestrial life. But here's the puzzle: if dinosaurs had these advantages, why weren't they immediately successful? Why did they remain minor components of Triassic ecosystems for perhaps 15 million years after their origin? The answer appears to be competition. The Triassic world was dominated by other groups, large predatory Raleigh-Suchians, some reaching lengths of 6 meters or more, were apex predators. Dinosaurs, heavily armored herbivores resembling armadillos crossed with crocodiles, were common plant eaters. Various groups of herbivorous decinodonts, survivors of the Permian extinction, still occupied many ecological niches, and there were numerous other archosaur groups, each competing for resources. Dinosaurs during this period were mostly small, mostly rare, and mostly unremarkable. They were waiting in the wings, so to speak, for their moment to shine. That moment came at the end of the Triassic period, approximately 201 million years ago, triggered by yet another mass extinction event. The Triassic-Jurassic extinction event was less severe than the Permian catastrophe, but it was still devastating, eliminating approximately 70 to 75% of all species. The causes remain debated, but again, massive volcanic eruptions appear to be the culprit, this time associated with the rifting apart of the supercontinent Pangaea and the formation of the Atlantic Ocean. The Central Atlantic Magmatic Province, as this volcanic region is known, released enormous amounts of carbon dioxide, triggering rapid climate change. The extinction was selective in interesting ways. Most of the large dominant archosaur groups were wiped out. The Raleigh-Suchians vanished. The Etosaurs disappeared. Most of the remaining therapsid groups perished. When the extinction ended, dinosaurs suddenly found themselves in a world with dramatically reduced competition. The ecological niches previously occupied by other groups were suddenly available, and the dinosaurs, with their efficient body plans and presumably their already diverse adaptations, rapidly expanded to fill them. This is what paleontologists call an evolutionary radiation. A rapid burst of diversification as a group adapts to newly available ecological opportunities. And the dinosaurs' radiation was spectacular. The Jurassic period, lasting from approximately 201 million to 145 million years ago, witnessed the transformation of dinosaurs from minor Triassic components to absolute rulers of the terrestrial realm. This was the age that captured our imagination. The era most people picture when they think of dinosaurs: massive long-necked sauropods, fierce predatory theropods, and bizarre ornithischians of every description. The Jurassic was a time of relatively warm, stable climate. Sea levels were high, creating vast, shallow seas and archipelagos. Pangaea was breaking apart, but the continents were still relatively close together, allowing dinosaurs to spread across the globe. Lush vegetation covered much of the land, providing abundant food for herbivores, which in turn supported diverse communities of predators. Let's begin with perhaps the most iconic dinosaurs of all, the sauropods. These are the long-necked giants that everyone recognizes, animals like Brachiosaurus, Diplodocus, and Apatosaurus. So, they represent one of evolution's most extreme experiments in body size, and understanding how they achieve such enormity requires examining multiple aspects of their biology. The largest sauropods reached truly staggering dimensions. Argentinosaurus, though it lived in the Cretaceous rather than the Jurassic, may have reached lengths of 30 to 35 meters and weights exceeding 70 metric tons. That's heavier than a fully loaded Boeing 777 aircraft. Even more common Jurassic sauropods like Brachiosaurus reached 25 meters. In length and weights of 40 to 50 metric tons. How did they achieve this size? The answer involves multiple factors working together. First, sauropods were highly efficient eaters. Their long necks allowed them to reach vegetation that other herbivores couldn't access, both high in the trees. And by sweeping their necks side to side across a wide area without moving their massive bodies. They didn't chew their food, instead swallowing it whole or with minimal processing, which saved energy and allowed rapid intake. Many sauropods had gastrolith stones in their stomachs that helped grind up plant material, essentially outsourcing the chewing process. Second, they had extremely efficient respiratory systems. Like modern birds, sauropods had a flow-through lung system with air sacs extending throughout their bodies, even into their bones. This provided superior oxygen uptake compared to the bellows-like lungs of mammals, and may have also helped cool their massive bodies. Third, their skeletal structure was marvels of natural engineering. Sauropod bones were often pneumatized, filled with air spaces that reduced weight without sacrificing strength. Their vertebrae featured complex systems of struts and hollows, achieving the structural properties of modern architectural designs. The overall effect was a skeleton that, while massive, was as light as possible given its strength requirements. Fourth, and perhaps most speculatively, they may have had elevated metabolisms compared to modern reptiles, though probably not as high as mammals or birds. This would have allowed them to sustain the activity levels necessary to consume the enormous quantities of food required to maintain their bulk. The ecological impact of sauropods was profound. They were landscape engineers, their feeding habits shaping the structure of forests. They created gaps in the canopy, allowing light to reach the forest floor and promoting undergrowth. Their dung, produced in prodigious quantities, fertilized vast areas. Their mere passage through forests created trails that other animals could use. They were, in a very real sense, ecosystem creators. But sauropods weren't the only dinosaurs diversifying during the Jurassic. The theropods, the bipedal carnivorous dinosaurs, were also radiating into a spectacular array of forms. The Jurassic saw the evolution of some of the most formidable predators ever to walk the earth. Allosaurus, perhaps the most famous Jurassic predator, was the apex predator of late Jurassic North America. At 8 to 9 meters in length and weighing up to 2 metric tons, Allosaurus was powerfully built with massive jaws filled with serrated teeth, up to 10 centimeters long. Its skull was specially adapted to withstand enormous forces, with flexible joints that allowed it to absorb impacts while attacking prey. Some paleontologists have suggested that Allosaurus hunted by making slashing bites with its upper jaw, using its neck muscles to drive its teeth into prey like a living axe. Evidence suggests Allosaurus sometimes tackled enormous prey. Sauropod bones have been found with Allosaurus tooth marks, and while it's debated whether these represent active hunting or scavenging, the presence of such marks indicates that Allosaurus at least fed on these giants. Some sites preserve multiple Allosaurus individuals together, leading to speculation about pack hunting, though this remains controversial. But not all theropods were large predators. The Jurassic also saw the evolution of numerous smaller theropods, some no larger than chickens. These small dinosaurs were probably already developing feathers, initially for insulation and display, though none had yet achieved powered flight. They were fast, agile, and increasingly intelligent, with large brains relative to their body size. One of the most remarkable small Jurassic theropods was Archaeopteryx, discovered in the famous Solnhofen limestone of Germany. Living around 150 million years ago, Archaeopteryx is one of the most important fossils ever discovered because it represents a transitional form between non-avian dinosaurs and birds. About the size of a raven, Archaeopteryx had teeth, a long bony tail, and clawed fingers on its wings, all clearly dinosaurian features. But it also possessed asymmetric flight feathers essentially identical to those of modern flying birds. Could Archaeopteryx truly fly? This quest generated The balance of evidence now suggests it was capable of at least some powered flight, though probably not as accomplished a flyer as modern birds. It represents a snapshot of the evolution of flight, capturing the transition in progress, and it proves beyond doubt that birds are living dinosaurs, the only lineage to survive the end Cretaceous extinction. The third major group of dinosaurs, the Ornithischians, also diversified during the Jurassic, though they wouldn't reach their peak diversity until the Cretaceous. Ornithischians, whose name means bird-hipped, were all herbivores and included many of the most recognizable dinosaurs: the horned ceratopsians, the armored ankylosaurs, the plated stegosaurs, and the duck-billed hadrosaurs. Stegosaurus, perhaps the most famous Jurassic ornithischian, was a bizarre-looking creature by any standard. About 9 meters long and weighing around 5 metric tons, it had a tiny head, a pronounced arch to its back, and was adorned with 2 rows of large, flat, roughly triangular plates along its spine, plus 4 long spikes on its tail. The function of the plates has been debated for over a century. They were too fragile to serve as armor. Current evidence suggests they functioned in thermoregulation and display, being covered with blood-rich skin that could flush with color. The tail spikes, called the thagomizer, were definitely defensive weapons. We have evidence of Allosaurus bones with puncture wounds that match perfectly with Stegosaurus tail spikes, proof that these herbivores could fight back effectively. The Jurassic world was also home to the first pterosaurs, large enough to be truly impressive. While pterosaurs had existed since the late Triassic, early forms were mostly small. By the late Jurassic, we see the evolution of forms like Pterodactylus and the larger Rhamphorhynchus, with wingspans exceeding 1 meter. These flying reptiles occupied ecological niches similar to modern seabirds and bats. But they were not dinosaurs, instead representing a separate branch of the Archosaur family tree. In the seas, various marine reptiles thrived. Ichthyosaurs, dolphin-like reptiles that had evolved from terrestrial ancestors, were common. Plesiosaurs, with their long necks and 4 flipper-like limbs, cruised the oceans. Enormous plesiosaurs like Liopleurodon were apex marine predators. But again, none of these were dinosaurs. Dinosaurs, with very few exceptions, remained terrestrial. By the end of the Jurassic, dinosaurs had achieved total dominance of terrestrial ecosystems. They occupied every major ecological niche. There were dinosaurian herbivores ranging from tiny ornithopods to gigantic sauropods. There were dinosaurian carnivores from chicken-sized hunters to 10-meter apex predators. There were specialized insectivores, omnivores, and possibly even some that fed on fish. Their diversity was spectacular, their abundance overwhelming, and they were just getting started. The Cretaceous period, lasting from 145 to 66 million years ago, was the longest period of the Mesozoic era and represented the absolute peak of dinosaur diversity, abundance, and ecological dominance. If the Jurassic was impressive, the Cretaceous was extraordinary. The world of the Cretaceous was dramatically different from the Jurassic. The supercontinent Pangaea had broken apart, and the continents were drifting toward their modern positions, though they hadn't reached them yet. The Atlantic Ocean was young but widening. South America and Africa were separating. India was an island continent drifting northward toward Asia. This continental fragmentation had profound effects on dinosaur evolution, as populations became isolated and evolved independently. The climate was even warmer than the Jurassic, with no ice caps at either pole and sea levels far higher than today. Much of what is now land was covered by shallow seas. Forests extended into polar regions, and evidence suggests that even in the Arctic and Antarctic, which experienced months of winter darkness, the climate was temperate enough to support lush vegetation and diverse dinosaur populations. The Cretaceous also witnessed one of the most important botanical revolutions in Earth's history, the rise of flowering plants, or angiosperms. For most of the Mesozoic, vegetation had been dominated by ferns, cycads, conifers, and ginkgos. But in the early Cretaceous, approximately 125 million years ago, flowering plants appeared and rapidly diversified. By the end of the Cretaceous, they dominated many ecosystems. This transformation affected dinosaurs profoundly. Flowering plants grow faster and are generally more nutritious than gymnosperms. Many have specialized structures like fruits, seeds, and tubers that are energy-rich. The radiation of flowering plants appears to have driven corresponding radiations in herbivorous dinosaurs, particularly the ornithischians, and in the insects that pollinated the flowers. The Cretaceous saw the evolution of the most famous dinosaur of all, Tyrannosaurus rex. Living at the very end of the Cretaceous, approximately 68 to 66 million years ago, Rex was one of the largest terrestrial carnivores of all time. At 12 to 13 meters in length, standing 6 meters tall, and weighing between 7 and 9 metric tons, it was a creature of superlatives. Rex possessed the most powerful bite force of any terrestrial animal that has ever lived. Biomechanical studies estimate a bite force exceeding 6 metric tons, strong enough to crunch through bone. Its teeth, some reaching 30 centimeters in length, including the root, were thick and banana-shaped, designed to prevent breaking while biting through bone. Fossilized tyrannosaur dung contains bone fragments, and damaged hadrosaur bones show that Tunch rex regularly bit through them while feeding. Its sensory capabilities were extraordinary. Rex had excellent vision with forward-facing eyes, providing binocular vision and depth perception superior to that of modern hawks. Its sense of smell was exceptional, with olfactory bulbs proportionally larger than those of any other dinosaur. Some scientists suggest it could smell carrion from kilometers away. Its hearing was also acute, capable of detecting low-frequency sounds. Recent discoveries have revolutionized our understanding of T-Rex. We now know that, like most other theropods, Rex had feathers, at least when young, though large adults may have lost them as they grew, due to heat regulation issues. We know that Rex grew rapidly, reaching adult size in about 20 years. We know that despite its fearsome reputation, Rex was probably an opportunistic hunter and scavenger, eating whatever meat it could obtain, whether from live prey or carrion. But T-Rex wasn't the only impressive tyrannosaur. Tarbosaurus from Asia was nearly as large. Earlier tyrannosaurs like Albertosaurus and Gorgosaurus, while smaller, were still formidable predators. And recent discoveries from China have revealed numerous early smaller tyrannosaurs, many clearly covered in feathers, showing the evolution of this remarkable lineage. The Cretaceous also witnessed the evolution of the most diverse group of herbivorous dinosaurs, the hadrosaurs, or duck-billed dinosaurs. These ornithischians evolved a remarkable feeding adaptation, dental batteries, tightly packed arrays of hundreds of interlocking teeth that created grinding surfaces, perfect for processing tough plant material. As teeth wore down, they were continuously replaced by new ones growing underneath. A single hadrosaur might go through thousands of teeth in its lifetime. Hadrosaurs became incredibly abundant and diverse in the late Cretaceous. Species like Edmontosaurus reached lengths of 12 meters and were probably the most common large herbivores in North America. Many hadrosaurs evolved elaborate cranial crests, hollow structures extending from their skulls. These crests functioned as resonating chambers, allowing hadrosaurs to produce low-frequency sounds for communication. Different species had differently shaped crests that would have produced different sounds, possibly allowing species recognition. Evidence suggests hadrosaurs were highly social, living in large herds. Bone beds containing thousands of individuals have been discovered, possibly representing herds that died together during floods or other catastrophes. Hadrosaur eggs and nests show evidence of parental care, with adults staying with young to protect and possibly feed them. The ceratopsians, or horned dinosaurs, also reached their peak in the late Cretaceous, while early ceratopsians from the Jurassic and early Cretaceous were small bipedal creatures. Late Cretaceous forms like Triceratops were massive quadrupeds with enormous skulls adorned with horns and a large frill extending backward from the head. Triceratops, living alongside T-Rex in the latest Cretaceous of North America, was one of the last and largest ceratopsians. At 9 meters in length and weighing 8 to 9 metric tons, it was built like a biological tank. Its skull alone reached over 2 meters in length, making it proportionally the largest skull of any land animal. The 3 horns, 2 over the eyes and 1 on the nose, were formidable weapons. The frill, while probably primarily for display and species recognition, also provided protection for the neck. Evidence of healed wounds on Triceratops skeletons shows they fought each other, probably for mates and dominance, locking horns much like modern bighorn sheep. We also have evidence of T. rex attacking Triceratops. Some Triceratops bones show T. rex tooth marks, and one spectacular specimen has a horn damaged in a way consistent with a T. Rex bite. The Cretaceous landscape witnessed epic battles between these titans. The ankylosaurs, armored dinosaurs covered in bony plates and often equipped with tail clubs, also thrived in the Cretaceous. Ankylosaurus, the largest and last of the ankylosaurs, was 7 meters long, 2 meters wide, and covered in thick armor. Its tail ended in a massive bony club that biomechanical studies suggest could deliver devastating blows, capable of breaking bones. Imagine the scene: a hungry T-Rex approaching an ankylosaurus. The herbivore crouches low, presenting its heavily armored back. The tyrannosaur tries to flip it or find a vulnerable spot, but the ankylosaur's armor is too complete. Then the ankylosaur swings its club, and if the blow connects with the tyrannosaur's leg, it could shatter bone. The tyrannosaur retreats, seeking easier prey. But perhaps the most remarkable Cretaceous dinosaurs were the smallest ones, the advanced Maniraptoran theropods that were evolving increasingly bird-like characteristics. These included the dromaeosaurs, popularly known as raptors, made famous by Jurassic Park, though dramatically oversized in that film. Velociraptor from late Cretaceous Mongolia was only about 2 meters long, half of that being tail, and weighed perhaps 15 kilograms, about the size of a turkey. It was covered in feathers, had long arms with grasping hands, and possessed a large sickle-shaped claw on each foot. Despite its small size, Velociraptor was probably a formidable predator. Using its intelligence, speed, and that distinctive killing claw to tackle prey, the famous Velociraptor specimen locked in combat with Protoceratops, both preserved in death, provides dramatic evidence of how these small predators lived and died. The Velociraptor has its sickle claw embedded in the Protoceratops' neck, while the herbivore has the predator's arm trapped in its jaws. They apparently killed each other and were then suddenly buried, perhaps by a collapsing sand dune, preserving this moment of mortal combat. For 75 million years, larger dromaeosaurs included Deinonychus from early Cretaceous North America and Utahraptor from the same time and place. Utahraptor reached 6 meters in length and weighed perhaps half a ton, large enough to pose a threat to mid-sized dinosaurs. Evidence suggests some dromaeosaurs may have hunted in groups, though whether this represents true cooperative hunting or just aggregations of solitary predators attracted to the same prey remains debated. Cretaceous. The Cretaceous also saw dinosaurs push into unusual ecological niches. Spinosaurus from North Africa was a bizarre giant that may have been semi-aquatic, feeding on fish. Species. At 15 to 16 meters long and weighing up to 7 metric tons, it was perhaps the largest predatory dinosaur. It had a sail-like structure on its back, long crocodile-like jaws filled with conical teeth perfect for catching fish, and surprisingly short hind legs. Recent discoveries have revealed that Spinosaurus had a flexible, paddle-like tail, dense bones that would have helped it stay submerged, and proportions suggesting it might have propelled itself through water using its tail. Like a gigantic crocodile, the idea of an enormous semi-aquatic predatory dinosaur challenges our traditional conceptions of dinosaur ecology. Therizinosaurs were another bizarre group, theropods that evolved to become herbivorous. With huge bodies, long necks, tiny heads, and enormous curved claws, reaching up to 1 meter in length, they looked like nothing else. The claws, initially thought to be weapons, were probably used to pull down branches for feeding. The diversity of Cretaceous dinosaurs is almost overwhelming. There were tiny ones like Microraptor, a 4-winged gliding dinosaur from China, no larger than a crow. There were gigantic ones like Argentinosaurus, possibly the largest land animal ever, weighing 70 to 100 metric tons. There were armored ones, horned ones, crested ones, long-necked ones, and every conceivable variation in between. Dinosaurs had adapted to every terrestrial environment. They lived in steaming tropical lowlands, temperate forests, arid deserts, and even polar regions. They ranged from solitary to highly social, from fast runners to slow walkers, from fish eaters to bone crunchers. They had evolved complex behaviors, advanced parental care, sophisticated communication, and possibly even intelligence approaching that of modern birds. By the late Cretaceous, dinosaurs had been the dominant land animals for over 135 million years. They had weathered numerous climatic changes, adapted to continental drift, and continuously evolved new forms. There seemed to be no reason why their reign should not continue indefinitely. But 66 million years ago, everything changed. A crater approximately 180 kilometers wide was excavated in seconds. Shockwaves pulsed outward through the Earth itself, triggering earthquakes far more powerful than any in human experience. The impact ejected trillions of tons of material into the atmosphere and beyond, some reaching escape velocity and being flung into space, some arcing back down to Earth as molten spherules that heated the atmosphere to oven-like temperatures. Mega tsunamis, waves potentially over a kilometer high, radiated outward across the oceans, sweeping away coastal ecosystems. The seismic shocks triggered volcanic eruptions and possibly displaced enormous volumes of seafloor methane. Within hours, the entire planet was affected, but the immediate effects, catastrophic as they were just the beginning. The truly devastating consequences unfolded over the following days, months, and years. Enormous quantities of sulfur from the vaporized rock formed sulfuric acid aerosols in the atmosphere, and the impact had ejected so much fine dust that sunlight was dramatically reduced or even completely blocked over much of the planet. The result was an impact winter. Temperatures plummeted. More critically, photosynthesis became impossible or drastically reduced. Plants began to die. With the base of the food chain collapsing, herbivores starved. With herbivores dying, carnivores followed. The collapse cascaded through entire ecosystems. Recent research has revealed the impact occurred in possibly the worst possible location. The Yucatan rocks contained unusually high concentrations of sulfur. Had the asteroid struck almost anywhere else, less sulfur would have been vaporized. The atmospheric effects would have been less severe, and the extinction less catastrophic. It was, in a terrible sense, an extraordinarily unlucky strike. How do we know all this? The evidence is written in the rocks, in a thin layer of clay found at the boundary between the Cretaceous and Paleogene periods, and called the KPG boundary. This layer, found in rocks around the world, contains extraordinary concentrations of iridium, an element rare in Earth's crust, but common in asteroids. The discovery of this iridium anomaly by Luis and Walter Alvarez and their colleagues in Ichenju by Bashers, provided the first strong evidence for an impact. Subsequent discoveries have only strengthened the case. The Chicxulub crater itself, though buried under younger sediments, has been mapped using geophysical techniques. Rocks from the boundary contain shocked quartz and tektites, glass spherules that form only under the extreme pressures of impacts or nuclear explosions. Layers indicate massive widening. The evidence is overwhelming and unambiguous. A catastrophic asteroid impact occurred at precisely the time non-avian dinosaurs went extinct. But was the impact the only cause? Recent research suggests the picture might be more complex. The end Cretaceous also coincided with massive volcanic eruptions in India, forming the Deccan Traps. These eruptions were releasing enormous quantities of carbon dioxide and other gases, causing climate change and ocean acidification. Some scientists argue that these volcanic eruptions were already stressing ecosystems before the impact, making species more vulnerable to extinction. Others suggest the impact itself may have intensified volcanic activity on the opposite side of the planet through seismic shock waves. The debate continues. But most evidence suggests that while the Deccan volcanism may have contributed to environmental stress, it was the asteroid impact that delivered the final fatal blow. The extinction was selective, in fascinating and informative ways. All non-avian dinosaurs died out, from the massive Tyrannosaurus to the small dromaeosaurs. Pterosaurs, which had ruled the skies for over 150 million years, vanished completely. Large marine reptiles, including mosasaurs and plesiosaurs, disappeared. Ammonites, shelled cephalopods that had been diverse and abundant for hundreds of millions of years, went completely extinct. But not everything died. Small mammals survived, probably because they could burrow underground, hide from the immediate catastrophe, and subsist on roots, seeds, and carcasses. Some birds survived, probably small, generalist species that could eat seeds and could thus survive the collapse of the food chain. Crocodilians made it through, likely because they could go long periods without food, and their aquatic habitats provided some protection. Turtles survived for similar reasons. Many fish, amphibians, and insects persisted. The extinction was strongly size selective. Generally, animals weighing less than about 25 kilograms had better survival chances. This makes sense. Smaller animals need less food, can hide more easily, and can survive on more diverse food sources. Larger animals, with their enormous caloric requirements, would have starved quickly as ecosystems collapsed. The fossil record from immediately after the impact is haunting. In North America, where we have the most complete record, there is a clear boundary in the rocks. Below it, dinosaur fossils are abundant and diverse. Above it, nothing. No dinosaurs, no pterosaurs, no large animals at all. The world had been emptied. What did that immediate post-impact world look like? Based on the fossil evidence and climate modeling, we can reconstruct the scenario. The sky would have been dark for months, possibly years. As dust and aerosols blocked the sun, temperatures would have plummeted with freezing conditions even in the tropics. Dead and dying plants and animals would have littered the landscape. Fires would have burned out, leaving vast areas of charred devastation. The few surviving animals would have huddled in whatever refuges they could find, subsisting on whatever food remained. Gradually, over months and years, the dust settled and sunlight returned. Plants began to recover. First, opportunistic species like ferns that produce enormous numbers of spores and can colonize disturbed ground quickly. Indeed, the fossil record shows what paleontologists call a fern spike, a period when fern spores dominate the pollen and spore record, indicating that ferns had taken over landscapes denuded of other vegetation. Slowly, ecosystems began to rebuild. But they were fundamentally different from what had existed before. The niches previously occupied by dinosaurs remained vacant. The surviving mammals, freed from competition and predation by dinosaurs, began to diversify and increase in size. Within 10 million years, the first large mammals had evolved. Within 25 million years, mammals had diversified into forms occupying most of the ecological niches previously held by dinosaurs. But one group of dinosaurs did survive, and they would eventually become the most diverse and numerous group of land vertebrates. 18. The birds. Birds are dinosaurs, specifically highly derived theropods, most closely related to dromaeosaurs and troodontids. Their ability to fly, their small size, and their relatively advanced metabolisms allowed some species to survive when their non-avian relatives perished. Today, there are approximately 10,000 species of birds, far more species than there are mammals. They occupy every continent, including Antarctica. They range from tiny hummingbirds weighing less than 2 grams to ostriches weighing over 100 kilograms. They have adapted to virtually every terrestrial environment and many aquatic ones. They can fly, run, swim, and dive. Some can hover, some can soar for days without landing, and some cannot fly at all. When you see a bird, you are seeing a dinosaur. When a hummingbird hovers at a flower, a dinosaur is feeding. When an eagle soars overhead, a dinosaur is hunting. When chickens peck at grain in a farmyard, dinosaurs are foraging. The age of dinosaurs never truly ended. It just took a different form. The story of dinosaurs, from their humble origins in the Triassic to their catastrophic end at the close of the Cretaceous, offers profound insights into evolution, ecology, and the nature of life on Earth. Their 180 million year reign demonstrates that success in evolution is not about being the strongest or the most intelligent, but about adapting to changing conditions and opportunities. So, dinosaurs succeeded initially because they had anatomical features that gave them slight advantages in the post-Permian world. Their upright stance, efficient locomotion, and other characteristics allowed them to outcompete other groups. But they flourished because of their extraordinary capacities for diversification. Throughout their long history, dinosaurs evolved into an astounding variety of forms, adapting to virtually every terrestrial ecological niche. Consider the range, from the massive 100-ton Argentinosaurus to the crow-sized Microraptor, from the bone-crushing Tyrannosaurus to the fish-eating Spinosaurus, from the armored Ankylosaurus to the fleet-footed Ornithomimids, from the elaborately crested Parasaurolophus to the horned Triceratops. This diversity wasn't just in form, but in behavior, ecology, physiology, and life history. Recent discoveries, particularly from China, have revolutionized our understanding of dinosaur biology. We now know that many dinosaurs, perhaps most theropods and some ornithischians, were covered in feathers or feather-like structures. This discovery fundamentally changed how we envision these animals. The fearsome velociraptor wasn't a scaly reptile, but was likely covered in feathers, giving it more in common visually with a predatory bird than a lizard. Studies of growth rates, determined by examining growth lines in bones, similar to tree rings, have revealed that dinosaurs grew rapidly when young, in some cases gaining several kilograms per day. Rex, for instance, went through a teenage growth spurt where it gained about 2 kilograms every single day for several years. This rapid growth required enormous food intake and suggests active, probably elevated metabolisms. The question of dinosaur metabolism has been debated for decades. Were they cold-blooded like modern reptiles, or warm-blooded like mammals and birds? The evidence increasingly suggests a more nuanced answer. They were probably mesothermic, with metabolic rates intermediate between typical reptiles and typical mammals. Some dinosaurs, particularly smaller theropods, may have been fully endothermic, warm-blooded, while larger species may have been gigantothermic, maintaining elevated body temperatures through their sheer size. Rather than active metabolic heat generation, brain size relative to body size, called the encephalization quotient, varies considerably among dinosaurs. Generally, theropods, particularly smaller ones, had relatively large brains suggesting greater intelligence. Some estimates place troodontids, small theropods from the late Cretaceous, as having brain-to-body ratios approaching those of modern birds, Muke, suggesting they might have been quite intelligent by dinosaurian standards. And larger dinosaurs like sauropods had relatively tiny brains, but this doesn't necessarily mean they were stupid, merely that their behaviors were probably less complex. The study of dinosaurs has also revealed much about fossilization and the incompleteness of the fossil record. Despite finds of dinosaur species, paleontologists estimate we have discovered perhaps only a small fraction of the total species that existed. Most organisms never fossilize. They must die in the right place, usually underwater or in sediment-rich environments. They must avoid scavengers. They must be buried quickly. The sediments they are buried in must not be destroyed by geological processes over millions of years. And finally, those rocks must be exposed at the surface, where paleontologists can find them. Given these requirements, it's remarkable we have found as many dinosaur species as we have, but it also means that for every dinosaur we know about, dozens or hundreds of others existed and left no trace. Entire ecosystems have vanished without leaving evidence. Our understanding of dinosaur diversity, comprehensive as it may seem, is based on a fragmentary, biased sample. This incompleteness extends to our understanding of dinosaur behavior, physiology, and ecology. We can infer much from bones, from preserved trackways, from rare exceptional fossils, preserving soft tissues or stomach contents, from comparisons with living animals, and from biomechanical modeling. But there is much we simply cannot know. What colors were dinosaurs? We have some evidence from preserved melanosomes, cellular structures that contain pigments, suggesting some small theropods were black, brown, or reddish. But for most dinosaurs, coloration remains speculation. Did dinosaurs make sounds? Almost certainly, given that modern archosaurs, birds, and crocodiles are quite vocal. Hadrosaur crests likely functioned as resonating chambers for sound production. But what did they sound like? We can model it, but we cannot know with certainty. How did they behave socially? Evidence of herding, nesting, and possible pack hunting suggests complex behaviors, but the details remain mysterious. Did they play? Did they have individual personalities? How did parents interact with young? We can speculate based on modern, but dinosaurs were unique and may have behaved in ways unlike anything alive. Today, despite these limitations, the science of paleontology continues to advance. New technologies are revealing information impossible to obtain before. CT scanning allows researchers to examine the internal structure of fossils without destroying them. Geochemical analysis of bones can reveal diet, growth rates, and body temperatures. Computer modeling can simulate how dinosaurs moved, how their bones responded to stress, and how they functioned as living animals. Perhaps most importantly, our understanding of birds as living dinosaurs has provided a living model for interpreting extinct forms. When we want to understand how a theropod might have behaved, we can look at birds. When we want to know about respiratory systems, parental care, or vocalization, birds provide insights. This connection between past and present has enriched both paleontology and ornithology. The extinction of non-avian dinosaurs also offers sobering lessons for the present. It demonstrates that even the most successful, diverse, and dominant groups can be wiped out by sudden catastrophic events. No amount of adaptation, no degree of ecological success provides immunity against bad luck. The dinosaurs hadn't failed evolutionarily. They were extraordinarily successful. But when a 10-kilometer asteroid happened to strike the Earth at a moment when extensive volcanism was already stressing ecosystems, survival came down to factors like size, diet flexibility, and the ability to ride out harsh conditions. Today, we face our own potential catastrophe, not from asteroid impacts but from human-caused environmental change. Climate change, habitat destruction, pollution, and other human impacts are driving what many scientists call the sixth mass extinction. Species are disappearing at rates perhaps 1,000 times higher than background extinction rates. While current extinction rates don't yet approach those of the great mass extinctions of the past, the trajectory is worrying. The difference, of course, is that this time the cause is not an asteroid or volcanic eruptions, but a single species, us. And unlike dinosaurs, we have the intelligence to recognize the threat and potentially to mitigate it. Whether we will do so remains an open question. The scientific study of dinosaurs, paleontology, has its own fascinating history. Dinosaur fossils have been found throughout human history, often interpreted as dragons, giants, or monsters in myth and legend. But the scientific recognition of dinosaurs as a distinct group of extinct reptiles is surprisingly recent, dating only to the Ichenbabite scissors. The term dinosaur, meaning terrible lizard, was coined by Sir Richard Owen in Ichenbabite Scissor R to describe Megalosaurus, Iguanodon, and Hylaeosaurus, three large fossil reptiles discovered in England. These early discoveries sparked enormous public and scientific interest. Dinosaur fossils became prized finds, leading to what has been called the Bone Wars, particularly the rivalry between American paleontologists Othniel Charles Marsh and Edward Drinker Cope in the late 19th century. This rivalry, while sometimes unethical and destructive, resulted in the discovery of many dinosaur species and enormous advances in paleontological science. Marsh and Cope together described over 130 new species of dinosaurs. Their discoveries, particularly in the western United States, revealed the richness of late Jurassic and late Cretaceous dinosaur faunas. The 20th century saw the globalization of dinosaur paleontology. Major discoveries were made in Mongolia, China, Argentina, Africa, and Antarctica. Each new discovery, the Mongolian expeditions of the Ichenjobite Arcers, led by Roy Chapman Andrews, discovered the first dinosaur eggs and revealed Asian dinosaur faunas. Chinese discoveries, beginning in the Ichenjobite Bashers and accelerating through the Ichenjobite Choshers and Erzhens, have been particularly revolutionary, revealing feathered dinosaurs and transforming our understanding of dinosaur biology. Technology has transformed dinosaur hunting. Satellite imagery helps identify promising fossil-bearing formations. GPS allows precise mapping of find sites. CT scanners reveal internal structures. Isotope geochemistry provides information about diet and climate. Computer modeling allows virtual reconstruction of extinct animals. The field has evolved from fossil collecting to a sophisticated multidisciplinary science. Today, new dinosaur species are being discovered at an unprecedented rate, roughly one new species every 2 weeks. On average, many of these discoveries are from previously underexplored regions. China, Argentina, and Mongolia have been particularly productive recently, but discoveries continue even in well-explored areas. New species are still being found in North America and Europe, sometimes in museum collections where fossils were collected decades ago but never fully studied. Each discovery adds detail to our understanding. Some finds are spectacular, complete skeletons, fossils with preserved soft tissues, trace fossils showing behavior. Others are fragmentary, a few bones, perhaps just teeth. But even fragmentary finds can be informative, adding data points to our understanding of dinosaur diversity and distribution. The process of discovering, excavating, preparing, studying, and publishing on a dinosaur fossil can take years or even decades. Field work is physically demanding, often conducted in remote areas with harsh conditions. Excavation must be painstakingly careful to avoid damaging fragile fossils. Large specimens may require years of preparation in laboratories to remove surrounding rock matrix. Study requires comparing the fossil to known species, determining its relationships, and describing its unique characteristics. Publication in peer-reviewed scientific journals is essential, allowing other scientists to evaluate the findings. The process is rigorous, requiring detailed descriptions, photographs, measurements, and anatomical comparisons. Once published, the specimen ideally becomes available for study by other researchers, allowing verification and further investigation. Museums play a crucial role in dinosaur science, housing collections that represent the primary data of paleontology. Museum specimens can be studied repeatedly, allowing new technologies to be applied and new questions to be asked. Specimens collected a century ago continue to yield new information as analytical techniques improve. Public displays in museums also serve the vital function of education and inspiration. Dinosaur exhibits are among the most popular museum attractions, drawing millions of visitors yearly. They inspire children to become scientists, they foster public interest in science, and they provide opportunities to communicate complex scientific concepts to broad audiences. The study of dinosaurs also illustrates how science progresses. Early ideas about dinosaurs were often wrong. They were initially imagined as slow, stupid, tail-dragging reptiles, evolutionary dead ends that failed and went extinct. This view persisted well into the 20th century, but as evidence accumulated, interpretations changed. The dinosaur renaissance, beginning in the Echingiobite lichens and Echingiobite tirachures, led by paleontologists like John Ostrom and Robert Bakker, reinterpreted dinosaurs as active, possibly warm-blooded animals. This view is now mainstream. Dinosaurs are understood as highly successful, remarkably diverse, and often quite advanced in their adaptations. The discovery of the dinosaur-bird connection, initially controversial, is now firmly established. The evidence is overwhelming. Birds are theropod dinosaurs, specifically members of the Manatauran group, most closely related to dromaeosaurs and troodontids. This connection has profound implications for how we understand dinosaur biology and for how we classify living birds. Scientific debates continue on many aspects of dinosaur biology. Were they warm-blooded? Evidence suggests yes, at least for many species, but details remain debated. Did they care for their young? Evidence increasingly suggests yes for many species, but exactly how and for how long remains uncertain. How fast did they move? Trackways and biomechanical models provide estimates, but uncertainty remains. These debates are a healthy part of science. They drive research, inspire new analyses, and gradually refine our understanding. The important point is that these debates are evidence-based. Scientists don't simply argue opinions, they present data, perform analyses, and build arguments that can be tested and evaluated. Beyond their scientific importance, dinosaurs have captured human imagination like few other extinct animals. They appear in literature, films, television, art, toys, and popular culture generally. This cultural fascination is worth examining because it reveals much about how we relate to nature, to the past, and to science itself. Part of the appeal is obvious. Dinosaurs were enormous, often dangerous-looking, and utterly extinct. They combine the fascination of large animals with the safety of complete extinction. Children in particular seem drawn, perhaps because dinosaurs are large and powerful yet can be safely studied and imagined without risk. The cultural image of dinosaurs has evolved alongside scientific understanding, though often with considerable lag. Early depictions in the 19th century showed dinosaurs as sluggish, rather toad-like creatures. The famous Crystal Palace sculptures, created in the Echingiobite Wursers, while scientifically advanced for their time, look crude and inaccurate today. They depicted Iguanodon as a heavy quadruped with a horn on its nose. We now know Iguanodon was primarily bipedal and that the supposed horn was actually a thumb spike. The early 20th century saw dinosaurs depicted more dynamically, but still as essentially giant reptiles. Films like the original King Kong from Echingiobite San, while entertaining, showed dinosaurs as rather clumsy, slow-moving creatures. This reflects the scientific understanding of the time, but seems quite dated now. The Iten-Jobite Licurses and Iten-Jobite Tirages dinosaur renaissance changed scientific thinking, but took time to influence popular culture. The Iten-Jobite Jusersan film Jurassic Park represented a watershed moment, depicting dinosaurs as fast, intelligent, and bird-like. While the film took liberties with science for dramatic purposes, it fundamentally changed how the public envisioned dinosaurs. Suddenly, dinosaurs were dynamic, fascinating, and more alien than ever. Subsequent films, documentaries, and other media have continued this trend, though accuracy varies widely. The Walking with Dinosaurs documentary series attempted to portray dinosaurs as scientifically accurately as possible while telling compelling stories. More recent series like Planet Dinosaur and Prehistoric Planet have benefited from even more advanced knowledge and technology. However, popular culture often lags behind or deviates from scientific understanding. The Jurassic Park film franchise, while scientifically groundbreaking in Iten-Jobite Jusersan, has become increasingly outdated. We now know that Velociraptor was covered in feathers, that Tyrannosaurus couldn't move as fast as depicted, and that Dilophosaurus didn't spit venom or have a neck frill. These inaccuracies persist in popular culture because they have become iconic. This highlights a tension between scientific accuracy and cultural inertia. Once certain images become established, they resist change even when science advances. The scaly, scale-covered velociraptor of Jurassic Park persists in many people's imagination, despite clear evidence for feathers. Dinosaurs also appear frequently in children's media, from picture books to animated series. These depictions range from scientifically informed to wildly fantastical. Some, like the animated series Dinosaur Train, make genuine efforts to be educational. Others use dinosaurs simply as familiar characters without concern for accuracy. Both approaches have value. One educates while the other simply entertains and builds familiarity. The naming of dinosaurs reveals interesting cultural patterns. Scientific names are typically Latin or Greek, describing anatomical features, honoring discoverers, or referencing discovery locations. But these names often enter popular culture and take on meanings beyond their etymological origins. Tyrannosaurus rex, meaning tyrant lizard king, sounds appropriately fearsome even to those who don't know Latin. Velociraptor, meaning swift thief, sounds sleek and dangerous. Some dinosaur names are unfortunately difficult or tongue-twisting, which may limit their popular recognition. Pachycephalosaurus, meaning thick-headed lizard, is scientifically descriptive but quite a mouthful. In contrast, simple names like Allosaurus or Stegosaurus are easier to remember and pronounce. Dinosaurs have also become symbols and metaphors in modern language. Calling something or someone a dinosaur implies being outdated, unable to adapt, headed for extinction. This metaphorical use is somewhat ironic, given that dinosaurs were actually remarkably successful and adaptable for over 170 million years. The metaphor reflects the outdated view of dinosaurs as evolutionary failures, rather than the modern understanding of them as highly successful. Commercial uses of dinosaurs are ubiquitous. Toy dinosaurs are staples of toy stores. Dinosaur-themed products range from clothing to home decor. Natural history museums often feature dinosaurs prominently, knowing they draw visitors. Theme parks and attractions capitalize on dinosaur popularity. The economic value of dinosaur appeal is substantial. This commercialization has complex effects on science. On one hand, popular interest in dinosaurs drives funding for research, creates public support for museums in paleontology, and inspires future generations. Many professional paleontologists trace their career choice to childhood fascination with dinosaurs. On the other hand, commercial pressures can sometimes compromise scientific accuracy or lead to conflicts over fossil ownership and access. The question of who owns fossils, particularly in countries with private land ownership, remains contentious. In the United States, fossils found on private land belong to the landowner and can be sold commercially. This has led to situations where scientifically important specimens are sold to private collectors, potentially making them unavailable for research. The most famous case involved Sue, a remarkably complete T.P. Rex skeleton that was the subject of legal battles before being purchased by Chicago's Field Museum for over $8 million. In contrast, many countries have laws declaring fossils to be national patrimony, prohibiting export and requiring that finds be made available to scientists. Both systems have advantages and disadvantages. Private ownership can incentivize fossil hunting and provide landowners compensation. Public ownership ensures scientific access, but may reduce motivation for discovery. These issues reflect larger questions about science, public access to knowledge, and the value we place on natural history. Dinosaurs, as charismatic exemplars of extinct life, sit at the center of these debates.